Here are properties 2 and 3 of the exponential distribution. Property 2 is uniqueness, and property 3 concerns the unit exponential distribution. Here's property 2. The exponential distribution is the only continuous distribution with the memoryless property. So that is to say, this is the only distribution with a constant hazard function that is continuous, and you can look all you want for another distribution to try to have this property. You won't find that distribution. The exponential is the only one that is a continuous distribution having the memoryless property. Now, the only discrete distribution with the memoryless property is the geometric distribution. We encountered the geometric distribution back in chapter 3. Here is property 3, and it says the following. If t is exponentially distributed with parameter lambda, then the random variable lambda times t is exponential with a parameter of 1. An exponential random variable with lambda equals 1 is often referred to as a unit exponential random variable, and you will see that again in the next property. Here's property number 4. If t is a continuous non-negative random variable with cumulative hazard function capital H, then capital H of t is exponential 1. Now, one thing that you have not seen before here is you have never seen a capital T put into a cumulative hazard function. We always put a lowercase t in there, so what's the story? If t is any continuous non-negative random variable, which is to say it could be Weibull, it could be log normal, it could be log logistic, any distribution you want, and you take that random variable t and you transform it by putting it into its own cumulative hazard function h, then that new random variable will be unit exponential, and that's property number 4. 4 notes here. This is mathematically equivalent to what is known as the probability integral transformation. This is a big result in probability and is really the basis for something in simulation known as random variate generation. Here's the probability integral transformation. If you take a random variable t and transform it by its own cumulative distribution function, then that will be uniformly distributed between 0 and 1. This probability integral transformation leads to what is known as the inverse CDF technique for generating random variates, and all you have to do is take a uniform 0-1 random variable u, plug it into its inverse CDF, and that will give you a random variate t. The property 4 at the top of the page here leads to an inverse CHF technique for random variate generation. Inverse CHF stands for inverse cumulative hazard function. The idea here is if you take a unit exponential random variable, and that's what's underlined here, and you plug that unit exponential random variable into its inverse cumulative hazard function, that will have the distribution of interest. Both of these techniques, the inverse CDF technique and the inverse cumulative hazard function technique, apply to both Monte Carlo simulation and to discrete event simulation. Here's an example of applying property 4. Let t have the Weibull distribution with survivor function e to the minus lambda t to the kappa. Lambda is a positive scale parameter. Kappa is a positive shape parameter. Using the 5 by 5 matrix, and the entry there is capital H of t is equal to the opposite of the natural log of S of t, you can find the cumulative hazard function for the Weibull distribution as lambda t raised to the kappa power. Now, if you look at the formula on the previous slide, we have to invert that cumulative hazard function. So one way to do that is simply set it equal to y and solve for t. And you solve for t by raising both sides of this equation to the 1 over kappa power, and then dividing by lambda. And that gives you h inverse of y is 1 y to the 1 over kappa divided by lambda. What this says is if you can take a unit exponential random variable, and this is just using the formula on the previous page, third bullet down, there's your unit exponential random variable, and you plug that into the inversed cumulative hazard function, this is one way to generate a Weibull variate where U is uniformly distributed between 0 and 1. That can be used in Monte Carlo simulation and discrete event simulation. Here's the geometry behind this particular type of variate generation. On the horizontal axis, we have time. On the vertical axis, we have the cumulative hazard function. And here is the cumulative hazard function for the Weibull distribution. Well, if I generate a unit exponential random variable, and in this case it looks like we generated maybe 2.8 or 2.9, but that's being generated right here. Its expected value is 1 because we have a unit exponential random variable, but in this particular picture we got one that's a little higher than usual. We got one at 2.8 or so. If you go across to the cumulative hazard function and down, that's equivalent to inverting the cumulative hazard function. And this gives you a random variate t, which is approximately 1.7. Now keep in mind that there's a difference between a random variable and a random variate. A random variable might be exponential, Weibull, log logistic, etc. A random variate is a realization or an instantiation of that particular distribution. And in this case, we get a single value t, which is a Weibull random variate.